Hi, and welcome to our 11th session on kinematics. So let me know if you can see my screen in a second. It should be on now. And just before we start, if you are in AISL, then this is not for you. So this is not part of the AISL course. So not for AISL. Lucky you. Then if you are new here, welcome. I'm Ashley from Miss IB Maths, collaborating with Exam Dojo for these bootcamp sessions. We have our 11th session today. The past 10 sessions are still on the playlist if you want to watch them. And if you would like the notes and exam questions for those sessions, you can DM me at Miss IB Maths on Instagram. I am an IB Maths tutor, teacher, and IB examiner. I see a question. We don't have any planned for the chi-squared tests, but we do have a session, I think one more session that nothing is planned. So we were wanting to see if anyone wanted anything specifically. So I will definitely have a look at doing the chi-squared. We can take a look at that. So watch this space. All right. Yeah, I'm Ashley from Miss IB Maths, IB examiner, teacher, and tutor. And you're welcome. Today we're going to be doing just an introduction to kinematics, having a look at some tips and things, then doing some worked examples, and then we're going to do some exam questions, past paper exam questions. So to start with a little warm-up. What do the first and second derivatives of displacement time graphs give us? So if you're not a physicist, this topic might be a little challenging to understand. I'm not a physicist, so I can do the maths and apply the maths, but often it gets a bit trickier when you don't have the physics background. So hopefully I can make that a bit easier for you as well if you're not doing physics. Any ideas? The first and second derivatives, what do they give us of displacement time graphs? Anyone know? So they give us first derivative of our displacement graph gives us velocity. And the second derivative gives us acceleration. That's what we're going to be looking at. So as usual, just to start with, this is what you have in the formula booklet. They jump straight to acceleration. They say when you go from acceleration from the derivative of your velocity, from the second derivative of your displacement. S is not speed. Not speed. A lot of people who don't do physics think S might be for speed. S is displacement. So we have acceleration, velocity, which is speed, and displacement. Then also when we're wanting to find distance from a velocity graph, we have absolute value of the velocity, and for displacement, we just have the normal velocity integral. So this is because, well, we'll talk about a bit more about this later, but displacement can be negative, whereas distance can't be. So just a reminder that absolute value makes all things positive because we're talking about distance, but we'll get more into that in a little bit. So just to show you, we have, let's say this is like a restricted x squared graph, right? Because time is on all of our x-axes on kinematics. Starting at 0, we can't have negative time. So we can have negative velocity, but we can't have, and we can have negative displacement, but we can't have negative time. So it's always going to start from 0 and go on to however much we need in the problem. So this is just a restricted you can see it kind of goes like that, the x squared graph, but we're not taking that portion of it because that is not realistic in real life. You can't have negative time. So here's an x squared graph. Then when you differentiate that, the velocity graph, you get 2x, which is then just a straight line. And when you differentiate that to get acceleration, you just get 2, just a constant line, y equals 2. So linear graph, this is y equals, and let's actually say dy by dx and d2y by dx squared to have proper notation. So you can see how the graph is changing as we go from each derivative to the other. So the tip that I will give you, I see a question that says the B velocity. Was that answering the previous question, perhaps? If that's another question, just let me know, but maybe you're answering a question before. So the easiest thing to remember with kinematics is a diagram like this. So if I take this as my S graph, S of t, this is my displacement with time over here, always. Then I differentiate and I get my velocity graph. And then also time, I differentiate again and I get my acceleration graph. If I'm going this way, I'm differentiating. So, all right, therefore differentiating. If I want to get from displacement to velocity, I've got to differentiate. If I want to get from velocity to acceleration, I've got to differentiate. But if I'm going the other way, I'm going to integrate. So this can be the best way to remember things when you are not sure, do you need to differentiate? Do you need to integrate for which one? Well, you think I've been given velocity and I need to find the distance or displacement. That means I need to integrate because I'm going up. But if I needed to get acceleration from velocity, I'm going to differentiate because I'm going that way. So often just drawing a little sketch like this, remembering that differentiating is going down and integrating is going up, can be really helpful. And then in terms of notation, let me just show you here. Let's say we have S of t and we find the derivative. We get the first derivative and the second derivative. Well, we can also call this, like we were saying, this is velocity. And then that can be the first derivative of velocity. That's also possible to call it like that. So these velocity and the first derivative of displacement are the same. And then we can also go from velocity to, I want to be on the same level, we go to acceleration. So these are just the different ways. So acceleration can also be the second derivative of displacement, just in case you get different notations. Oh yes, that was the answer to the question. Nice. And so these will be really helpful when we're trying to figure out how to answer the question. So yeah, here we have just a few of the ways that we can write it. And one other thing I wanted to say was, this is also if you're not really doing physics, the ms-1 can sometimes confuse some students that don't do physics. So if I have, in fact, let's go by my earlier diagram here. So if I'm measuring my displacement, distance or something, it's in meters. So then this one is in meters per second. It's because it's speed or velocity. So meters per second, we can also write and bring the s up to the top with a -1. So sometimes that's why you see it like that. You might also know meters per second like that. They all mean the same thing. And here it's meters per second squared, which we write as meters per second to the -2. So it's just because we bring that up, they're all equal. So it's just the unit of measurement. So don't get confused when you see these little -2s and -1s. It just tells you in which unit you're working. Then displacement and distance. A lot of people get confused with this. Displacement can be negative. Distance can't be. I can never have a negative distance. So distance is always going to be positive, and it's the full distance I traveled, whereas displacement is how far I am from my origin, or how far I am from where I started. So that can sometimes be easier to show in a diagram. Excuse my very non-straight line. Let's say we go from 0 to 2 to 5. And I'm going to do distance in green. So let's say I'm a particle and I'm starting at 0. Then I'm traveling to 5. All right, so let's say my distance. I've traveled from 0 to 5, so I've gone 5 meters. And then I reverse to 2, so I've gone that way, and then I go back this way to 2. Well, I've traveled another 2 meters, even if it is backwards. So, sorry, 3. I've gone back to 2, so I've traveled 3 meters. So that means I've traveled 8 meters in total. That's my distance. Whereas displacement, I'm a particle starting at 0. I travel to 5. So my displacement, long word. I travel to 5. And then I've gone back to 2. But now I want to look at how far am I from where I started. I started at 0 and I'm ending at 2. So I've only gone 2 places. So that's why it's negative 3 meters. So my distance that I traveled was 8 meters altogether, but my displacement, where I went and where I ended, was only actually 2 meters from my start. So, excuse me, that is the difference between distance and displacement. So just to be careful with that. Then some important things to remember. If the question asks, on what intervals is the particle speeding up, or can you tell if the particle is speeding up, or is the particle speeding up or slowing down? You want to look at these things. So if velocity and acceleration have the same sign, i.e. both positive or both negative, they're V and A are both positive or they're both negative, then it's speeding up. But if they have different signs, so let's say that one's positive and that one's negative, or that one's negative and that one's positive, they're different, then the particle is slowing down. And then when your acceleration is equal to 0, that means your velocity is constant. So if you imagine you're a car just driving along the highway, if you are not putting your foot on the acceleration pedal, then you're just traveling the same speed. So, I mean, in a real life situation, you probably would end up slowing down if you're not on the accelerator. But if you're not accelerating, if your foot isn't on the pedal, you can assume the velocity is the same because we're not accelerating and we're not decelerating. So we're going the same speed, just a constant. So the particle still could be moving even if the acceleration is 0. Acceleration being 0 does not mean that we are at a stop. Okay, let's see with some worked examples. So a particle is moving along a straight line. Its displacement from the origin at t seconds is the following function. So my displacement function is given here, and obviously time is more than or equal to 0. Find the velocity function and find the acceleration function. So if I have let's do A and write that function again, then my velocity function is just the first derivative of my displacement. So that would be 3t squared minus 12t plus 9. And then my acceleration is the second derivative. So we have 6t minus 12. And there we go. I have my 3 functions. Then find the values of t when the particle is at rest. So think about what that means. When a particle is at rest, it has no speed. So when the speed, v of t, my velocity, is equal to 0, that's when it's at rest. So we set our velocity function equal to 0. So that's 3t squared minus 12t plus 9. I can divide all through by 3 to make this a bit simpler. And to find the values of t, I can graph it or factorize or use the quadratic formula, whichever method you prefer. So that would be, luckily 3 is a prime number, so we don't have too many options here. There we go. So t equals 1 or t equals 3. So the values of t when my particle is at rest is at 1 second and 3 seconds. Then find the velocity when t equals 4. So velocity again, I want my velocity function. I want for v of 4. So it'd be 3, 4 squared minus 12 times 4 plus 9. So that's 16. 3 times 16 is 48. 12 times 4 is also 48 plus 9. That's nice and easy. So 9, and we need to say the velocity is 9 meters per second. There we go. Then determine the direction of motion. So the direction of motion we can see by our velocity graph. So when the velocity is positive, we are moving in the positive direction. So that's what they mean by direction of motion. When our velocity is negative, you guessed it, it's in the negative direction. Quite straightforward. Just all these confusing physics words. Negative direction. So we need to determine the direction of motion. So basically we need to determine, is it positive or negative at t equals 2? So let's figure that out. So again, we need for velocity. So a lot of velocity questions here. 3, 2 squared minus 12, 2 plus 9. So that is 12 minus 24 plus 9. 12 minus 24 is minus 12 plus 9 gives us minus 3. Negative number, minus 3 meters per second. So our direction of motion, is in the negative direction. That's all they're asking. Because it was a negative number. Ooh, excuse my handwriting there. Okay. Let's see, what else do we have? Right, so that was differentiation when we're going from displacement to velocity to acceleration. Now, what about if we're going the other way? If they're giving us velocity and we want to find displacement, well, then we've got to go up the graph that I showed you at the beginning. We've got to figure out the opposite direction. So that means integration. So to find displacement, we have the integral of the velocity function, and don't forget plus c, our constant. If you have forgotten any integration, there'll be a session on it tomorrow at 5 p.m. CEST time. So we'll be going over that. So I'm not going to be going over integration now, but if you want some help with that, that will be tomorrow. Okay, so a particle has velocity, where is my thing, of 3t squared minus 4t. And we need to find s of t. So s of t will be given by the integral of this function, 3t squared minus 4t. If we have more than one term, we should put it in brackets, dt, because you're doing with respect to t. It's an indefinite integral, so we don't need any values here, any boundaries. And they've given us an initial condition here. So this initial condition gives us basically an x and y coordinate so that we can find our c, because this is going to give us a plus c, and so we'll need that to figure out what c is to give our final function. So let's integrate. So we're going to have 3t add 1 to the power and divide by the new power, minus 4t add 1 to the power and divide by the new power. And, well, Just used to doing that from definite integrals. And don't forget a plus c. There we go. So that is my s of t, but it's not complete because I need to know what c is. So this is where this comes in. We love it when they give us 0 because that's just going to make these disappear. Let me actually simplify this a little bit. T cubed minus 2t squared plus c. And let's substitute. So we're going to put 5 equals 0, because 0 cubed is just 0, minus this term will become 0 as well, plus c. So c equals 5. So we can write our lovely function now. S of t is t cubed minus 2t squared plus 5. There we go. So don't forget that plus c. I think the integrating part is easy, but people often forget to do the plus c. All right, let's try that with a definite integral. So we want to find the displacement from the velocity again. So we need the integral of that function. And now we're going on the interval 0 to 5. So they want to know over this time period, over the first 5 seconds, what is the distance that we've covered, the displacement. So again, we're just integrating because we're going from velocity to displacement. So that means integrating again. That means we have 5, 0, and 6 minus 2t, brackets again, because there's more than one term, and dt. If you have your calculator in this exam, you can just put that in and have that done for you. So let's see, what do we have? That's going to be 6t minus t squared, because I'm going to get 2 and divide by 2, so that just cancels out. I don't need to plus c because it's a definite integral. So I do put my brackets to show that I do have those boundaries. And I'm going to substitute 5. 6 times 5 minus 5 times just 5 squared. That's my first bracket. Minus, and now I substitute 0. 6 times 0 minus 0 squared. So what do we have here? 30 minus 25. And very nice, that's all just 0. So we get 5. And what was our unit? We wanted displacement, and we're in meters. So my displacement was 5 meters. If at any point something I do doesn't make sense, just put a message in the chat and I will happily go back and explain it. I think I was covering the screen a little bit, so hopefully now you can see. All right, but what if you want the distance? Because displacement can be negative, and that can mean that if I have an area, like I have this area plus this area plus this area, if that's a positive area, that's a negative area, and that's positive, I could get that this gives me a negative area. So I could get a negative displacement, which is fine. We allow that. Negative displacement is not a problem. However, if I want to find distance, remember that I'm going to want everything to be positive. So I'm going to need the absolute value of this part. So wherever the function is from this point to this point on this interval, I'm going to need to have the absolute value of that function because I want the full distance. I want this part, I want this part, and I want this part. Well, like I said, the positive part of it when it's reflected and absolute valued. So this is fine. That's just v of t on that interval from here to here. This is just v of t. I don't have to absolute value these, but to be safe, you can just absolute value everything to not make a mistake. And then I'm going to get the total distance covered without having to subtract anything. So here's my function. I have a velocity function and I need to find the total distance. These keywords here are really important. Distance, not displacement. Distance over the boundary between 0 and 4. So if I think of my, let me just go down a little bit. That function is a quadratic. So it's going to look like this. Where do we go through? 3, So something like that. All right, and we want from 0 to 4. So let's say, use a different color. No, it's all right. Let's say that that's our 4 and that's our 0. So we want between these two values. So we're going to want this area. That's our first area. We're going to want the absolute value of this area, and we're going to want this area. So these three areas we need to add up. But we need to find out these 2 points here, because I need to take it in 3 different parts. I'm going to need to find from 0 to whatever that value is, from that value to that value, and then absolute value that part, and then from here to here. Because if I don't absolute value it, I'm going to actually end up subtracting this area, but I want the full area. So let's see my function. V of t equals t squared minus 4t plus 3. So to find these values here of where I'm going to take my interval from, I need to set my graph equal to 0, because those are just my intercepts. So hence find the intercepts. So let's find those. We had a similar function already, so we're going to factorize the same. T minus 3 and t minus 1. So t equals 3 and t equals 1. So 1 is there, 3 is there. So my first integral, I'm just going to move up a little bit. Should I change colors? Yeah. My first integral will be from 0 to 1 of that function. 0 to 1 of v of t. And that is positive. But let's just absolute value it all. It can't hurt. Especially if you're not sure. If you can't think of the function in your head, just make it all absolute valued. Then I'm going to need to add that to this part, the part from 1 to 3. And this part I definitely need to absolute value. 1 to 3, v of t dt. And then the last part from 3 till 4. Sorry, my allergies are going crazy. Of v of t dt. So these are each of my 3 areas. So what is my the integral of v of t? So let's see. We have, I'm just going to write it here, there, v of t. So the integral of v of t, because I'm not going to write it out 3 times. V of t t squared minus 4t plus 3 dt. So that will give me t3 over 3, add 1 to the power, divide by that new power, minus 4t squared over new power 2 plus 3t, just tack on an extra t. I would need to add plus c usually, but because these are definite integrals, it's going to take care of that later. So I'm just going to leave that. So if this was a non-calculator paper, that would be pretty horrible, because you would have to put this function in and do that for each of these. But I'm just going to use my calculator for now for time-wise, and it's a bit laborious, but let's put that into our function. So it's also a good moment to show you how to do it on your calculator. So let me remember that, t squared minus 4t plus 3. So we want to press this little button over here, and there we go. We have our definite integrals. So the first one was from 0 until 1. If you have a different calculator and you want to know how to do it on yours, you can just pop me a message on Instagram, and I will give you a little tutorial for whatever your calculator is. So what we were t squared minus 4t plus 3, but let's use x. 4. No, I'm already forgetting it. T squared. So let's do x squared minus 4x plus 3. Okay, and I'm integrating with respect to my variable x. So there we go. 1.33333, which is 4 over 3. So let's keep it like that for now. So my first one here was 4 over 3. That's positive, so all good. Now let's do it for this one from 1 till 3. So I can go back at that and change just my integrals. So that was 1 till 3. See, negative, but we're absolute valuing it, so it's positive. Maybe I'll write that just to note it. And from 3 till 4, also, interesting, it's all equal, 4 over 3. So that is my total area under the curve. So 4 over 3 plus 4 over 3 plus 4 over 3 gives me 12 over 3, and 12 divided by 3 is just 4. So what was my question actually asking? Find the total distance traveled, and we were in meters. So the total distance traveled is 4 meters. So just to double check when the question asks, am I doing displacement or am I doing distance? If it's distance, make sure that you absolute value and break it up. If you're doing displacement, you can just go and do from 0 to 4. You don't have to split it up like that. And one more example, I think, before the exam questions. So when we're doing finding velocity from acceleration, just reminded that speed is the magnitude of velocity. So all speed is positive. Velocity can be negative. Velocity can be positive or negative, but speed is only positive. So if they ask for velocity or maximum velocity, remember that a negative value is fine. But if they're wanting speed, then it's always going to be the absolute value of the velocity. So that's quite an important point to note. All right, let's see with this one. So I have the acceleration is 6 minus 2t, and I need to find the velocity. So that means to find v of t, I'm going to need to integrate a of t. Because remember, if we're going back upwards, we are integrating from velocity to from acceleration to velocity. That's going back up, so we integrate. So what do we have? 6 minus 2t dt. That'll be 6t minus t squared. And now we do need a plus c because this is an indefinite integral, but they've given us a boundary condition here, which is great. So if I put v of, well, let's just immediately go in with my value of 3. 3 equals 6, 0 minus 0 squared. Love it when it's 0. So c equals 3. So therefore, my velocity function is 6t minus t squared plus 3. And there, done. Did I fully answer the question? Yeah, we just need to find v of t. Okay, let's try some exam style questions. So just to note before we start that this is a paper 1, so that means no calculator. Fun, no calculator. Okay. An object moves in a straight line. Its velocity is given by this function. A graph of v is shown in the diagram. So always very good to see what are you starting with? You're starting with a velocity function. Okay. And there is our velocity function, and it's between 0 and 5. Another thing that I like to do, just to make it really clear to myself that it's an ending boundary, is to just mark at 5 that this is the end. So this is the final point of my graph, because it looks like it's going on until infinity, but it's not. It's stopping at 5 because we're going from 0 to 5 seconds. So there we have our function. This is the graph we can see. So if you think about this in like a real life situation, that can really help to think about what's happening. Is I'm starting here with my velocity. It's positive, so in a positive direction. It's increasing. It reaches a maximum at x equals 1. Or sorry, at t equals 1. At 1 second, it reaches a maximum. That will probably be interesting. Then my velocity is decreasing. And then what happens here? my velocity goes from positive to negative. And what that means is it changes direction. So my particle at 0 seconds, let's say here is 0, here is 3, and here is 5. If we think about distance, my particle is traveling along, it's going this way. And then for the next 5 seconds, it's changed direction. So it's actually going backwards. I mean, on time, this looks a bit confusing, but it's changed direction. So it goes that way, and then at 3 seconds, it changes and goes back that way until it ends up at this point here. So when it crosses over on a velocity graph from positive to negative, that crossing over point means a change of direction, because here velocity is negative, but negative velocity just means the direction of motion is in the opposite direction. Okay, so that's before we've even looked at a question. We've just tried to see what's going on in the situation, and hopefully that will help us to answer some questions. So the graph of V has a local maximum point where t equals 1. We already talked about that. Maximum there, and intersects the t-axis at t equals 3. Determine the object's maximum velocity. So if I want maximum velocity, it's where the velocity is the biggest number. So that's going to be at the maximum. So if I want to do that, this is paper 1, so I don't have a calculator to check that. I need to figure out where this graph has a maximum. So shall I write that next to it? There isn't a lot of space. I'll write it here and then just label it. So that was question A. Was it? Okay, so maximum velocity is going to be at this point. That's the highest point. So if we write our function, v of t equals 30 plus 20t minus 10t squared. To find the maximum point of this graph, we need the first derivative. So let's find the derivative. We have, is there not an easier way to find it? There's a way easier way to find it. They've given us that the maximum is at t equals 1. So we just have to substitute. That's way nicer, because it's only 2 marks. So we just need to substitute for v equals 1. So 30 plus 20 times 1 minus 10, 1 squared. There we go. So that's 30 plus 20, which is 50, minus 10, so at 40. And what are we in? What units, meters per second? There we go. So our maximum is at 40 meters per second. That's our maximum velocity. Then they ask, what is our maximum speed? So remember that speed must always be positive, the absolute value. So if I'm looking at my graph, let's see. Here I have my maximum velocity, but when it goes here, it changes direction, but the speed is just the absolute value of this part. So I'm actually going to reflect that over my graph like that. See, when we do absolute value, we just flip it over the x-axis. So my maximum speed is actually up here. That's my maximum speed. And it's whatever this value is. Let's say that's v of 5 absolute valued, right? So we need to find the velocity at t equals 5, because that's the end point there. And then the absolute value of that. So 25 minus 10, 5 squared. So that's 30 plus 100. 5 squared is 25 times 10 is 250. So that gives us 130 minus 250. So that's 70 plus 50. So 120 minus 120. but we're absolute valuing it. So that equals 120 meters per, well, so that's our maximum speed. Let's just double check everything is good there. That was question AI and AII. Just write that in I and here. All right, so just a note about that it looks like that would be a maximum, but actually reflected when they're asking about speed is that one up there. Now, at t equals capital T, the object changes direction. So we already talked about this, that here at this point, the object changes direction because it goes from a positive velocity to a negative velocity. So that's at the point t equals 3. So the value of t is, I'm just going to write t equals 3. Nice 1 mark question. Find the distance, keyword here, distance, traveled by the object in the first 3 seconds. So again, remember we have a velocity graph and we're trying to find the distance traveled. So remember that if we're going from velocity to distance, we're going upwards. So that's integrating. And because it's distance, not displacement, it's the absolute value. So let's write our integral. We have the integral of our v of t dt and the absolute value of that from 0 to 3, because we want the distance traveled in the first 3 seconds. So from 0 to 3. And this was still a paper 1 paper, so no calculator for us. So we have 30 plus 20t. Let me write it all again. So 30 plus 20t minus 10t squared, was that it? The memory of a goldfish. dt. There we go. Everyone's still good? Now let's solve that. Right, so that will give us 30t plus 20t squared divided by 2 minus 10t cubed divided by 3. Oh, that's so mean of them to give us that without a calculator. Why do I feel like that's going to take ages? And then we put it from 0 to 3. So these brackets here, if you do the square brackets, are kind of just a universal way of saying we still have to go from 0 to 3. Let's simplify that a little bit. So 30t plus 10t, I don't know why my t is up there. I'm just going to move it over so I'm not blocking it for everyone. Plus 10t squared minus 10 over 3. T cubed, there we go, 0 to 3. And if I did that, you can see why this is a 4 mark question, because there's a lot going on in here. Can I be lazy and cheat and look at the mark scheme to get the answer here? Because no, shall I not? Okay, I won't be lazy. It's fine. So let's substitute 3. So 33, they all have t in them. So I know at least for that part, it's not gonna exist. Plus 10, 3 squared minus 10 over 3. 3 to the power of 3. There we go. And then I need to subtract it from all of this when I input 0. But when I put 0 here, that's 0, that's 0, that's 0. So it's just minus 0. So that's great, actually. So here we have 90. Here we have 90 again. This is a lovely, one of these 3's cancels out with that 3. So 3 to the power of 2 is 9 minus 90. Oh, that wasn't so bad in the end. So it equals 90. 90 what? We want a distance. Distance traveled by the object. So we were in meters. And the nice thing that we can see here from the graph is that the absolute value doesn't matter because this is all positive anyway. So if we were finding over this area, we would need to absolute value it, but for this area, we're fine. It's all positive. So we have meters. 90 meters is the distance traveled by the object in the first t seconds. So the first 3 from here to here. In fact, let me just clean this up a little bit. And I'll use red. In this 3 seconds, we traveled 90 meters. Okay. And that was question B. Then determine whether the object returns to its initial position during the time period 0 to 5, justifying your answer. So when our object is going, so it's traveled 90 meters in this direction, and then here it changes and it goes back. So for these 2 seconds, our object is going back to where it started. So the question is asking us, in these 2 seconds, does it go back to its original position? So what we're going to do is we're going to figure out how much distance happens in these 2 seconds. Because if we know that in these 2 seconds, it's more than this distance, then yes, it is going back to its original position. Because there it was going for 90 meters. That's my 90 meters. Then it stopped and it turned around. And for those 2 seconds, if it goes more distance, then it's past where it started. But if it goes back less than where it started, then we know that it does not return to its initial position. So we want to figure out from 3 to 5. Let's do it over here. Let's go and that's a bit aggressive. So we want to know from 3 to 5 of, well, it doesn't matter because whatever the answer is, we'll just take it. So Vt dt. We've done all of the hard work already, so I'm just going to go straight to answering that question. What are we at? This was our final 30t plus 10t squared minus 10 over 3t cubed. And now the only difference here is that we're going from 3 to 5. Oh my word. So this one looks like it's going to be a lot. So we need to substitute for t equals 5 and for t equals 3. And I'm definitely going to be lazy and cheat here and check what the answer is because that's going to take ages. So here you can see our answer. They've put in 5 and 3, and the final answer that they get is 3 minus 320 divided by 3. Minus 320 divided by 3. And that was in meters. So now if on my diagram, I'd gone 90 meters that way. And now I'm going 320 divided by 3. What is that? Like if we do 300 divided by 3. So it's just over 100, this number. So I've gone there and now I'm going back. I've gone back more than 100. So yes, I have passed my initial starting point where I started when I go backwards. So the answer to that question would be yes. What is an object? The object returns. Sounds like a movie title. The object returns to its initial position. Excuse me. Okay. Oop, covered my drawing there. Hope that's clear. How are we feeling? Is that making sense? I hope so. So in the mark scheme, we get marks for attempting to find certain things. You don't have to use the units. You don't lose marks if you don't use the units. It's a good habit to get used to. Also, it helps to keep you aware of what you're calculating, what you've already calculated. So I do recommend that you write it, but you won't lose marks for not writing the units. Yeah, often these attempts to find things are really nice. So if you don't know how to approach the question, if you see kinematics questions and you just freak out and think, oh my gosh, I have no idea what that means, attempt to do something. They often will say something like where t equals 1. So what you can definitely do is substitute t equals 1. We all know how to do that. What you can do when it says they want to find distance or displacement, you can integrate the function or differentiate the function. Even if you don't know what the question's asking, look out for all of these hints. So it's all littered with hints like maximum points, maximum speed, maximum velocity, changing direction, initial positions. They all carry the same kind of words that you learn what they mean when you do a few of these problems. But I don't think there's anything unexpected in the mark scheme or anything to note. I must say that's quite mean of them to ask in a non-calculated paper. That just takes ages. Anyway. All right, let's try another one. We still have time. So a particle moves in a straight line such that it passes through a fixed point O. Don't know where O is. At time t equals 0, okay? At t equals 0 is here, so that's our fixed point O. Moves in a straight line such that it passes through that, where t represents time measured in seconds after passing O. Is that definitely where O is? Yeah, that's where t equals 0. It's between 0 and 10. This is a velocity graph again. And it's given by 2 sine 0.5, blah, 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 blah. So there we go. Find the smallest value of t, so the smallest time, least time, when the particle changes direction. So changes direction, do you remember what that was from the previous question? Changes direction, what does that mean? Where can we see that the particle changes direction? And second question, how many points on this velocity graph at how many points does the particle change direction? Anyone know? Need to do a poll maybe. Okay, so here when it goes from negative to positive or positive to negative, so here it's negative, it's in a negative direction. The function is increasing, so not to be confused with that, but it's under the x-axis or the t-axis. So it's going from negative velocity to a positive velocity. That means it has changed direction. It was going that way, and now it's going this way. Then it keeps going that way in a positive direction, and then again here. It was going that way, and now it's changed to negative again. So now it's going that way. So at these 2 points, the particle has changed direction. Let's take those away. And they said find the smallest value of t. So did I cover a number there? No. So the smallest value of t will obviously be this one, because here the time is something like 6. So the t value here is way shorter. So we want to find out when this graph hits the t-axis. So when this is equal to 0, the smallest value of t. So we have v was 2 sine 0.5 t plus 0.3 t minus 2. So when this is equal to 0, 2 sine 0.5 t, and perhaps this is a paper 2 calculator. I should have checked that at the beginning, because it would be great to just graph this and then find that out. Let's see. Yes, it's paper 2, so we have a calculator. So instead of finding the derivative of this, I'm setting that equal to 0 to find the, no, that wouldn't work. We're going to graph it. Let's see, I want to graph. And I don't think it says anything about degrees or radians. So 2 sine 0.5x. Our calculators don't like t as a variable, only x. 0.3 t, x minus 2. Double check that I've got it correct. See, trig. Oh, fine. There we go. So they want to know, you can see we're here from -2 until 10. So let's actually just change our window so that we are, let's see, window settings, yeah. Let's go from 0 until 10. So we see the exact same thing. And from -2 until 2. Let's go -3 until 3. There we go. So now I see pretty much the same thing. Okay, so we wanted to know this value. When was that equal to 0? So we're finding an intercept. And I just need to choose my bound. 1.69. 3 significant figures. So when t equals 1.69, where are we in seconds? That is when I have the smallest value of t. The displacement of the particle is measured in meters from O. Find the range of values of t for which the velocity is positive. So velocity being positive, oops, not meant to do that. Velocity being positive is this area here. That's when it's above the t-axis. So from here, which was, we know that's 1.69, we've just found that, to this one. So they just want us to find this value now. And luckily we've still got our graph open, so we can do menu, analyze graph. The other 0, we want this one now. 6.12. 6.12 seconds. So we can say for, that was A, this is B. So between 1.69 and 6.12. And sorry, not X, I should say T. These are the range of values for which my velocity is positive. Now, find the displacement of the particle relative to O when t equals 10. Displacement is the whole thing. So all of this area, this is displacement, the area under the curve, because we're going from velocity back to displacement. So we're integrating. So I want all of these areas, but it is displacement, not distance. So we don't need to do absolute value. So I want to know when from the start, from 0 until 10, I want all of these values, but I don't need to do them separately and add them because it's displacement, not distance. I mean, they've lined up the question perfectly to ask us for distance because we've had to find these values here, but missed opportunity. So we're going to then take the integral because we're going from velocity to displacement and from 0 to 10 of our graph, 2 sine 0.5 t. And this is a calculator question, calculator paper. So we're definitely going to put this on our calculator. And dt. So let's do that. We want. I'm going to take my integral again from 0 to 10. gosh, this is going to take a while. 2. Should have actually copied it across. Sine 0.5. -0.3 minus 2 dx. Ooh, there we go. Minus 2.13. So the displacement of the particle, minus 2.13. And the fact that it's negative is fine because it's displacement. That makes sense. The area under the curve is more than the area above the curve, and that actually makes a lot of sense. And we're in seconds. No, we were finding distance. Meters, sorry. Velocity is meters per second. So that was the displacement, meters. All right, let's check our mark scheme. So we have the fact that you're finding those values, that 1.69, recognition that velocity is 0. So make sure that when you answer this question, you are doing it on your calculator, but you show this step. So even though I was not solving it myself, I showed that I knew that velocity is 0. That's when the value of t changes direction, when it's equal to 0. And I found that value of t. So that was an important step. That was 1 mark, just to show that. And then the other mark was my 1.69. So if you're doing things on your calculator, I really recommend that you are showing what you're doing, your steps as well. So you don't actually ever have to write, like in brackets, I use my GDC or I use my calculator. That's not helpful. What you should do is write down the things that you're assuming by using when you use your calculator. So we were finding the intercepts, x-intercepts, which means that we recognized that velocity was 0. So those kind of things you have to show mathematically. Then we had our range of values. This is not to 3 significant figures. So here it is, to 3 significant figures. You got 1 mark for each of those over there. No, it was A1 for both values. So if you had both values, that was your A1. And for the correct inequalities, you got your other mark. So if they say range of values, use your inequalities. You could also use like this, 1.69212. And it did include those values, so we should do square brackets. That's another way we could show our range. And then there are minus 2.13. Did I say minus 2.13? I did. Good. Okay. Then I think I might end there. How are we feeling about kinematics? Has this helped? Does it feel a little bit less confusing now? Would you like me to do one more question? It is 6:05 already, but so far I'm not managing to keep them within an hour. Yeah, this is a 17-mark question. 5 marks, 5 marks. This question, it seems like a lot, but it's not actually difficult. It's just because it's a paper 1. So that means you're doing a lot of the steps yourself and you're finding minimums and maximums. So that's what really the marks are coming from. So maybe I won't do the question, but I'll just go through what they're asking of you. So again, find the displacement of the object from the origin at t equals 1. So let's just have a look at the situation. We're going from 0 to 4. From 0 to 4, always spend some time familiarizing yourself with the graph. It helps a lot. 0 to 4 is there. So a hint again, see that there's a minimum here, the end point, and we're in a velocity graph again. We're really loving these velocity graphs. That's going to be reflected back up there. So that will be a maximum. That's going to be more than this maximum. Here we have a maximum. Here we have a minimum. This is what I'm seeing before I even start the question. And the object first comes to rest at t equals k. So the object would come to rest at this value. Would it? No, we don't know that yet. Oh yeah, it would be, because it's changing direction. So that's when the velocity is 0. So that would be the k value that they're speaking about. We can label all of these things on the graph before we've even answered the question or looked at the questions. So they say, find the displacement of the object from the origin at t equals 1. And have they given us any clues about t equals 1? No. But we could find displacement by taking the absolute value of the velocity, not the absolute value, because we're in displacement. So the integral is what I mean. We can take the integral of the velocity, and we want of the object from the origin at t equals 1. So from 0 to 1, we want to find out that velocity, that displacement. So we would set that up and work it out, and you can see we have a lovely function to work with here, but nothing crazy there. That's just 5 marks for all of the integrating you're going to do. Then find an expression for the acceleration of the object. So if you're doing acceleration from velocity, remember that's going down. So you're differentiating this to find acceleration. So acceleration would be the first derivative. Then find the greatest speed reached by the object. So speed, greatest speed, is going to be this one, remember? Because here's the greatest velocity. That's where it's the maximum velocity, but here is the greatest speed. So that will be the absolute value of v of t. And that value there would be at t equals 4. All right. So this one, write down an expression that represents the distance traveled by the object while its speed is increasing. This one I will go through. Do not evaluate the expression. So you don't have to answer it. When they say do not evaluate the expression, they just mean like make your expression and then leave it as it is. You don't actually have to solve it. So write an expression that represents the distance traveled by the object while its speed is increasing. So let's have a look. When is the speed of this object increasing? Let's use a different color. Let's use some red. So increasing. Here my speed, my velocity is going down. No, we are talking about speed. So that's going down. That's not increasing. But from here to here, between my minimum and my maximum, it's increasing. Is there another place where my speed is increasing? So my velocity is decreasing, velocity is decreasing, velocity is decreasing, but speed is absolute value flipped up. So between here and here, that absolute value of that function, my speed is increasing. So that's a little catch there. So speed increasing for that absolute value. So you would find here and here, whatever these values are, I think that you would have calculated them in a previous section, and between here and here. So the distance traveled is going to be, you're going to integrate between this area and this area. So don't forget here that you'll do your integral of the absolute value of v of t between k, that was k, and 4. And then you'll add it to, let's see, what were those values? We had to here t equals a third and t equals 2. So then for this area, that would be between a third and 2 of v of t dt. And that's positive already, so we don't need to absolute value that. And that would give us the whole distance when the speed is increasing. So that's another kind of question. Again, if you want to work through this and try this yourself, the mark scheme is attached as well, and you are more than welcome to try these out and send me your working, and I can tell you if you're on the right track or if you're correct or give you feedback. That's at Miss Ivy Maths on Instagram. Feel free to send me your questions. I'm happy to answer. Excuse me. Right, I think I will stop it there because it has been a while. Yeah, so like I said, state units in every answer. I think that it does help you just to be a bit clearer about what you're answering, and the examiner has a more positive experience when they're marking it, which is always a good thing. They say that examiners, they're obviously very impartial people, of course, but I think if you do all the things to help them, I know myself when I'm marking, the clearer it is, the easier it is, I think the better. Then I think we talked about quite a few of these things. Remember that speed is always not negative. Okay, so notes are there as usual if you want to go over more of these examples. There'll be a homework assignment that is meant to be session 11. Are there any questions at the moment? I hope that it is at least a little bit clearer and that you feel a bit more confident about approaching these questions. Really think about it in the real world sense. Like try and make it as like real to you as possible instead of just equations and graphs, because for kinematics, really thinking about it in a real sense helps you to think what's happening in the situation and what makes sense. Any questions at all? Give 30 seconds, maybe 10 seconds in case anyone's typing a question. Tomorrow we are going to have integration practice. So if any of the integration was unclear to you, we'll be working on that. And we're also going to be doing binomial theorem. So there's quite a few different ways that they can ask the questions in binomial theorem, and they often come up, and I really say binomial theorem is easy marks. So if you're not finding it easy, then hopefully we'll see you tomorrow. Okay, then thank you so much for joining, and I hope you have a lovely rest of your evening. Goodbye.